Hey guys, so today I'm going to be doing the 22 or sorry, not 20, 2009 exam, and to make it as realistic as possible, I'm going to time myself for 75 minutes, and I've never taken this before, so let's just see how I do. I mean, it's kind of old, it's like 12 years old, so it should not be super hard or anything, but let's see. So without further ado, okay, 1 hour 15 minutes, start. Okay, a 0.3 kilogram apple falls from rest through a height 40 centimeters on a flat surface. Upon impact, the apple comes to rest in 0.1 seconds, and 4 centimeters squared of the apple comes into contact with the surface during impact. What is the average pressure exerted on the apple during the impact? Well, we know first of all, pressure is force over area, and we know that force is the change in momentum with respect to time. I'm not going to use calculus since you don't need calculus, but so actually, okay, I messed up. Force is the change in momentum with respect to time, which is also mass times the change in velocity with respect to time, and this remains as the area. Okay, and then let's plug in the values. So 0.3 kilograms, it falls from rest. And then we know that G should then be GT since it falls from rest. And actually, it gives us a height. It doesn't give us at the time it takes to fall. So we would use another equation, V equals rad 2GH, which is just rad 20 times H, which it said is 40 centimeters, which is 0.4 meters. So we have rad 20 times 2/5, which is just 2 rad 2. So we have 0.3 times 2 rad 2, and then it comes to rest in 0.1 seconds. So this is over 0.1. And finally, 4 centimeters squared of the apple. And this is tricky. A lot of people are going to say, oh, wait, that's 0.04 meters. But remember, it's squared. So in reality, this would be 4 times 10 to the negative 4 meters squared. Yeah. And just to make this easier, I can actually multiply the top and bottom by 10 to the power 4, which is 10,000. So then I would get 3,000 over 2 rad 2 over 0.1 over 4. Okay, now let me just input this into my calculator. Okay, 3,000 times, actually I'll just put that as 20 root 2 and divided by 4. Okay, we're getting about 21,213 pascals. So B should be the correct answer. Okay. The following information is used for questions 2 and 3. 3 blocks of identical mass are placed on a frictionless table as shown. The center block is at rest. Blah blah blah. Okay, you can read it. Honestly, I'm not gonna read the fonts because I'm sure. I hope y'all can read it. Okay, so it's okay. So we have for this one we have the center block. Okay, so let's call this V1I and V2I, which is just 0, and then this is meaning V sub 3I. Okay, so, and right now we want to find what V2F is. So V2F is in the after this collision here. It should be just equal to 2m1. But actually, they're all the same mass, so I'll just say 2m over 2m times v1I. So then after the first collision, so let's just ignore this one, it should now be moving to this side at v1I. Okay, so yeah, because these cancel out. Okay then, so let's actually wait, let me read this. Oh wait, so these are actually moving at the same speed. So this is also v1I because this is identical speeds, which then means that the momentums half of these two should cancel out. Yeah, okay, so that means they either move back at the same speeds or they just touch and don't move. But all collisions are perfectly elastic, which means that the center block should be moving to the left. Yeah. Okay, okay, now we have to zoom they're all perfectly inelastic. If they're perfectly inelastic, then, okay, so let's look at this collision again, but this time as an inelastic collision. So we have mv1I equals 2m v final, which then means v final is just 1/2 v1 initial. And so these are both moving this way at that yeah. Okay, so the momentum, the total momentum, and this also has velocity v1I, but it's in the opposite direction. So we have 2m, but then we have times 1/2 v1I, yeah, minus m v1I, which means that the momentum should cancel out, so it should be at rest. And it should be left of its initial position, so this is wrong. Actually, no, sorry, it should be to the right. Okay, this is right, and you should be wrong. Alright, okay, so a spaceman of mass 80 kilograms is sitting in a spacecraft near the surface of the Earth. The spacecraft is accelerating upwards at 5 times the acceleration due to gravity. What is the force of the spaceman on the spacecraft? Well, first of all, we know Newton's third law means that the force of the spaceman on spacecraft is just the negative of the force of the spacecraft on the spaceman. So we can just find this, basically. And by negative, I don't mean it's literally negative, I just mean the vector points in the opposite direction. Okay, so, well, this is F equals MA, and so we have 80, and A has to be 5 times 10, so it should be 4,000. But wait, is it ask? Okay, there's actually a bit of ambiguity here. Does it mean it's at 5 times the acceleration, counting the Earth's acceleration, or not counting it? Um, yeah, okay. I think that they should have made it a lot more clear. I'm just gonna okay. If they're not counting the Earth's acceleration, then the answer would just be 4,000 units. If they are counting it, then it would really be moving at 6 times the acceleration due to gravity, so it would be 4,800 units. And this is actually pretty inconvenient because they just had to make both of these the answers. My gut's telling me that they're saying that we should count it, so yeah, 4,800 then, yeah. Okay. Oh man, I hate gravitation. Oh well. 3 equal mass satellites A, B, and C are in coplanar orbits around the planet as shown in the figure. The magnitudes of angular momenta of the satellites are measured about the planets L sub A, L sub B, and L sub C. Okay, so well, first of all, we know that L is just the rotational inertia times this, or it can also be written as MVR. And yeah. Okay, so this is interesting. They all have the same mass. Does it say if they all have the same velocity? It says nothing about the velocities. So, actually, yeah, I will do. Okay, I'll just get back to this one later. Yeah, I hate gravitation. Okay, an object is thrown with a fixed initial speed v naught at various angles alpha relative to the horizon. At some constant height h above the launch point, the speed of the object is measured as a function of the initial angle, which are the following best describes the dependence of v on a. Okay, so, well, we know that the equation for max height is v squared. What was it again? Okay, no, the range equation was the squared for both of them. Wait, no, oh wait, I think it's just v naught squared sine squared theta. I think it is over g, or is it over 2g? I'm trying to recall. Yeah, I think it's over g. Actually, it doesn't matter because it's just seeing how theta and the velocity are related. Okay, actually, let's see. And actually, they said this was the alpha. But so h is equal to v naught squared sine squared alpha over g. Okay, we want to isolate b, so we have gh over sine squared alpha is equal to v naught squared. So v naught is equal to 1 over sine alpha times gh. Okay, so okay, let's just try some angles. So if we did 0 degree, or if we did 0 degrees, then it would be undefined. If we did 30 degrees, we get 1/2, which means that this is 2 gh. If we do 45 degrees, we get rad 2 over 2, which means this is rad 2 gh. If we did 60 degrees, it's rad 3 over 2, which is 2 over rad 3 gh. So it seems to be decreasing. And then okay, and then if we make this 90 degrees, it'll just be 1 over, if it's 90 degrees, then it's just gh. So it's definitely decreasing. Hmm. Actually, no, it never really increases. So I think I'm gonna have to go none of the above. Okay, a bird is flying at a straight line initially at 10 meters per second. It uniformly increases its speed to 15 meters per second while covering a distance, yada yada yada. Well, we can just use one of the kinematic equations, which says that v squared is equal to v naught squared plus 2a times the displacement. So now if we plug in 15 squared is 225, which is equal to 100 plus 2 times a times 25, which means then that 125 is equal to 50a, which means that a is equal to 125 over 50, which is equal to 5 halves, which is equal to 2.5 meters per second squared. Okay, that was easy. A flat disk rotates about an axis perpendicular to the plane of the disk and through the center of the disk. Okay, so it looks like this, and then there's an axis like this, and it rotates. Okay, and then an angular velocity as shown in the graph below. Determine the angular acceleration of the disk when t equals 2 seconds. Well, I'll just be the slope because we know that it's just this, and we can just see then. So if we use this to represent the slope at 2 seconds, since it's like an equal distance from 2 on both sides, we can just basically use rise over run. So we know it goes down by 4 and then runs by 2. So we have negative 2 radians per second squared. At what net angle does the disk turn during the 3 seconds? Well, the acceleration we can see sort of constant throughout. So we can say that the net angle is equal to um, the initial angular speed minus 1/2 times that, which is 3 times the initial angular speed minus 9/2 times that. Uh, Actually, since we're saying that the angular acceleration is negative, we can still keep this as plus. Yeah, we have to be super careful with our signs. I mean, that's a general thing in math, but yeah, physics as well. Okay, so then W naught is, it says it's 4, so we have 12 plus 9 halves times negative 2, which is just 12 minus 9, which is 3. So 3 radians. Okay, let's see how we're doing on time. Not bad. So less than 20 minutes. And almost 10 questions. I think I skipped one, but whatever. A person standing on the edge of a fire escape simultaneously launched 2 apples, one straight up with a speed of 7 meters per second, the other straight down at the same speed. How far apart are the 2 apples 2 seconds after they were thrown? A zoom igniter has hit the ground. Well, all we have to do for this is just create 2 kinematic equations for each of the apples. So this will be for the apple that is thrown straight down. So we have a negative 7. Um, Actually, you know what? To make this easier, let's say that down is the positive direction. Yeah, okay, so down is positive. Which means then that the second apple would actually have an initial velocity of 7t, and gravity would be positive, so it would be like that. Okay, and then the first apple would be -17, and the acceleration is still the same, so it's this. If we plug in, okay, so we plug in 2 for each of them. Okay, so the position for this one should be 14 plus 1 half times 10 is 5. 5 times 4 is 20. 14 plus 20, so 34. Technically, it's -34, but I'm saying down is positive, so whatever. Here, it should be -14 plus 20, which is 6. Subtract the 2, we have 28 meters. And so we have C. A 2.25 kilogram mass undergoes an acceleration as shown below. How much work is done on the mass? How much? How do I do this? Okay. Hmm. It's acceleration with respect to position. This is, yeah, I'm not quite sure how to, oh wait. Actually, the mass is constant. Okay, so what we can do then, W is equal to the dx. But since the mass is constant, this can, I think we can do this, I don't know. Does it work? We shall see. Okay, so, see, 2.25, so that's 2.25 which is basically just the total area. So this area here is 4. This area here is 2 times 4, so it's 8. This area here is 4 times 4 divided by 2, so it's also 8. And then this area here is, sorry about that. Okay, so this area here is, well, the height is 2, well, technically -2. The base is 4. 4 times -2 over 2 is -4. So we have 16. Huh. That is not a choice. Okay, oh wait, I have to multiply by 2.25. Okay, I almost forgot. So it's actually 16 times 2.25, which is 36. So it should be a, yeah. Okay, Batman, who has a mass 100 kilograms, he do be kind of thick though, climbs the roof of a 30-meter building and lowers one end of a mastless rope to his sidekick Robin. Okay, so shot. We have this absolute unit weighing in at 100 kilograms, and okay, just one end of a mastless rope. And this unit, who is not as awesome, is 75 kilograms. And how much total work has he done? Well, the work is just force times displacement. In this case, Robin's force of gravity acting on Robin is 715 units. Let's see, 10 plus Robin was a mass of 75 kilograms. Okay, and then times 30 meters. I don't think any of these answers are matching up. Where am I messing up? How much work has Batman done after robbing Zombie Roof? Wait, what? Um, wait, what? Okay, I don't quite understand it. Batman was a mass of what, 100 kilograms. Climbs the roof, floors one end. Um, yeah, okay, I'm just gonna get back to this one. Okay, so Lucy, mass 33.1 kilograms. Henry, mass evenly spaced. Okay, so let me. Who exerts the most torque? Um, so that seesaw balances. Okay, let's draw it out. So we have some seesaw, and they're evenly spaced. Okay, so it would not make sense for um, so actually Henry would have to be here so that the torques balance, and Mary is here. Yeah. Oh, wait, it should just be Lucy then, because if Henry was on the same side as Lucy, well, Lucy is exerting the most torque. But Lucy, Henry. Yeah, okay, it should be Lucy. Um, a wooden block, if I'm pegged by mass 12, a speeding bullet with mass m at initial speed v naught collides with the block at time t equals 0 and embeds in s speed. The system consisting of the block and bullet, which quantities are conserved between -10 and 10 seconds. Okay, well, this is wrong because, well, there's gravity and there's also tension. So, yeah, that's wrong. This would also be wrong because if the block moves this way, there's going to be a horizontal component to the tension, which and force is a change in momentum with respect to time. So the momentum would still change. Angular. Hmm. Okay, so it looks like it is either D or C. Yeah, it couldn't be C actually because a lot of energy would be lost. There's heat, and there are no external torques acting on the system. Oh, just gravity, but gravity would actually. Okay, so it's again. Yeah, okay. I think it would have to because it's either D or E, and so we know that um, sum of external torques is just the change in angular momentum with respect to time. So if there is an external torque acting on this, then it would have to be E. And yeah, there would be because even if this moves here, it won't go all the way because there's going to be gravity, which is exerting a torque. So it would have to be, and it's not C because energy is less than heat. A 22 kilogram suitcase is dragged in a straight line at a constant speed of 1.1 meters per second across a level airport floor. On the way to the 40th International Physics Olympiad in Merida, Mexico. The individual pulls with one times like 100 newton force along the handle, which makes an upward angle of um, 30 degrees with respect to the horizontal. Okay, so if I had to draw this, 100 newtons goes terribly drawn, and 30 degrees. Okay. Okay, and since it's at a constant speed, we know that the friction has to cancel out with whatever the horizontal component of this 100 newton force. So then we have 100 cosine 30 degrees is equal to the friction, which is just equal to mu mg, which is just equal to 220 mu. 100 cosine 30 is just equal to 50 rad 3, so therefore mu is 50 rad 3 over 220. Okay, 50 times rad 3 divided by 220 is about 0.394. Okay, let's see how we're doing on time. Not bad. We haven't even used up half of our time. We're still looking good. Okay. Two identical objects of mass M are placed at either end of a spring of spring constant K. Okay, so these are both mass M, and this is spring constant K. And the whole system is placed on a horizontal frictionless surface. At what frequency does the system oscillate? That is an excellent question. Okay, so let's first look at it in terms of displacements. If we move this by delta x, and we move this by delta x, then the total restoring force would be 2k delta x, which means that 2k would be the the new spring constant. So then it will be this, I think. Yeah, I think it should just be rad 2k over m. That because there are two masses, and yeah. Actually, wait, no, because there'd also wait. Actually, then it would be 2m, which means it would just be k over m. so never mind. Yeah, okay, I almost got tricked there. Okay, you are given a standard kilogram mass and tuning fork. I have no idea what that is. That is calibrated in hertz. You're also provided with free collection of laboratory equipment, but none of it is calibrated in SI units. You do not know the values of any fundamental constants. Which of the following quantities could you measure in SI units? Um, huh, I don't know. This is that's a good question. Um, I think it should be D because, well, hertz is a unit for frequency, which I believe is 1 over 2 pi times k over m, and we want to find spring constant, so that's f squared, which is equal to 1 over 4 pi squared times k over m, so that's 4 pi squared f squared is equal to k, so I think it should be d. Okay, okay, this looks a bit tricky. A simple pendulum of length L is constructed from a point object of mass m suspended by a massless string attached to a fixed pivot point. A small peg is placed at distance 2L over 3 directly below the fixed pivot point so that the pendulum would swing. What? So, wait, this is a bit confusing. Oh, wait, never mind. I think I get it. Okay, so that the pendulum would swing as shown in the figure below. The mass is displaced 5 degrees from the vertical and released. How long does it take to return to its starting position? Okay, so we know that the total period is 2 pi times L over G. Yeah, and then, okay, so the problem specified that this distance here is 2L over 3. Okay, so, but then this is the period we want to find for only half of the distance traveled. So then the new period would actually just be pi times L over G plus pi times, um, this is L over 3. So L over 3G, which is then just pi times L over G times the quantity of 1/3 plus 1 over root 3, or root 3 over 3, which actually I didn't need to rationalize, but it is E. Okay, not bad. How are we? Okay, we're chilling on time. We used up barely a little over half our time, and we're actually almost done. Okay, a certain football quarterback can throw a football a maximum range of 80 meters on level ground. What is the highest point reached by the football if thrown this maximum range? Okay, actually we just need another range equation for that, which is v naught squared sine 2 theta over g. Okay, and then the problem said this is 80. Um, okay, it says what is the highest point reached by the football if thrown this maximum range? Um, That is okay. So actually, then we need to use the height equation now, which is, I believe it's v naught squared sine squared theta over I think it's either g or 2g. Yeah, I'm going with 2g, which means then that uh, we just have to. Okay, so this actually we can change this a little. So it's 2v naught squared sine theta cosine theta over g. Okay, wait. Okay. Um. Hmm. I guess. Well, the range we know is maximized at 45 degrees. Actually, yeah. Okay, so that means that the angles have to be 45 degrees. Okay, and we know then that we just have to do multiply this by 4 and shoot, okay. You have to multiply it by 4 over sine theta, but then cosine theta. Wait, let's see. Okay, so then this should be sine theta cosine theta. Yeah, that would be 2 sine theta cosine theta over g. Yeah, okay, so I'm gonna have to multiply it by this, and well, this is root 2 over 2, this is root 2 over 2. So we then get that this is equal to 2 times max height. Wait, no. 4 times, okay, I cannot read, I am sorry. Okay, 4 times the max height is 80. So the max height has to be 20. I wasted a ton of time because I had a brain freeze, but at least we solved it. Okay, nice. Consider a completely inelastic collision between two lumps of space goo. Nice, okay. So, lump 1 has mass m and originally moves directly north with speed v naught. Lump 2 has mass 3m and originally moves directly east with speed v naught over 2. What is the final speed of the masses after the collision? Ignore gravity and assume that the two lumps stick together after the collision. So, then this is 3m v naught over 2. Okay, so then, first, I guess let's look at, oh wait, and it's moving east at v naught over 2. Okay, so I guess first let's look at the horizontal stuff. So the initial horizontal momentum would be 3/2 v naught, and then since everything sticks together, it would be 4m times v final. Actually, let's do vx final because this is horizontal. So then we know that vx final would have to be 3/8 v naught. Yeah, okay. Great, now let's look at the y component of the momentum. So now we have mv naught, and then after they collide, the total mass is 4m again. And let's close vy naught and vx naught to avoid confusion. 4m times vy final, which then would be, actually no, I don't need this x naught and y naught because it's still moving like, or these don't have components. Okay. So then well, we just get v naught over 4. So vyx is equal to v naught over 4. So then we would just have to use the Pythagorean theorem, and we would have 3/8 squared plus by 1/4 squared v naught. And I'm too lazy to actually do that, so I'm gonna actually yeah, it's asking for any seconds, so I have to. Okay, so that's 9 over 64 plus 1 over 16, which is 4 over 64. So 13 over 64 v naught, which is just root 13 over 8 v naught. Okay. Two stars orbit their common center mass as shown in the diagram below. The masses of the two stars are 3m, and the distance between the stars is d. Okay. What is the gravitational potential energy of the two-star system? Nice. Well, that's a good question. I think it's just, well, over d, it's m times 3m, so it should be negative 3gm squared over d. I don't know, it just seems something doesn't feel right. It seems too easy, so I'm wondering if I should consider the center of mass or not. Okay, I'll just leave this as my answer. Yeah. Okay, determine the period for the star of mass 3m. Okay. Well, star mass 3m. Okay. Okay, so period is just 2 pi r over v, which is just 2 pi r over root gm over r. Which is just 2 pi r root r over root gm. Wait. Actually, no, I should just do 2 pi r root r over gm. Okay. And by m I mean 3m. So actually, let's put in 3 gm. Okay, so now we have to find the distance between the center mass and this. And we can do that by, okay, so let's call this x position 0. So then we have m times 0 plus 3m times d over 4m, which then means that this is 3/4 d, and using basic subtraction, and this should be d over 4. So for r, we can plug in d over 4, and if we do that, we get pi over 2d times d over 12gm. Nice. Okay, and then we can move this in to get d cubed. So now we have pi over 2 root d cubed over 12gm. Still doesn't look like the choices, but I can multiply 4 to the bottom, so now I have pi times d cubed over 48gm, and we can take out 16, so that would be 4. So then we have pi over 4 times d cubed 3gm, which is Still not one of the answers. Where did I mess up? Okay, so hmm. Yeah, definitely messed up somewhere, but I do not know where. Okay, so let's go back here. Okay, this is correct. This is correct. This is correct. Actually, wait. This is, yeah, okay. Let's actually let's try it in 2 pi root r cubed over 3 gm and then substitute d over 4 for r when it's in here. So then we have 2 pi times d cubed, and 4 cubed is 64, 64 over 3 is 192, so 192 gm. 192 is 16 times 12, or no, 64 times 3. Wait, so I'm still getting the same answer, that is. Okay, I'm gonna get back to the sleeper. A mass is attached, actually, let's check the time. Okay, we have 1/3 of the original time left. A mass is attached to an ideal spring at time t equals 0. The spring is at its natural length, and the mass is given by an initial velocity. Period of the ensuing one-dimensional simple harmonic motion is t. What is the power delivered to the mass by the spring first? A maximum or what? What is the power delivered to the mass by the spring first? Wait. Okay, the wording is weird. Oh wait, no. At what time is the power delivered to the mass by the first? A maximum. Power is force times velocity, and we know force is k delta x. And velocity is well, we know that x is this. So then the velocity should be negative this. Okay, so let's see. Actually, the period is t, so t is 2 pi m over k. And let's actually, I think I might need to take another approach to this. Okay, so because the power is force times velocity, and the force is the greatest at the one of the amplitudes. Well, the velocity is the greatest at the middle. Uh, Actually, let's see if we can find the velocity in terms of the amplitude. So 1/2 ka squared is equal to 1/2 mv squared. Ka squared is equal to mv squared. So v is equal to, or v max rather, is equal to k over m times a. Okay, so you can plug this in. So then we have p is equal to kx times root k over m a, which means then that p is the greatest at one of the amplitudes, because that's when x would be the highest. So then, if this was the starting point and a full period was the time it took to return to the starting point, then it would go here, and then back here, and then back here. So that is, wait, no. Yeah, okay, so that's 1, 2, 3, 4. So t over 4, 1, 2, 3. Yeah, t over 4 would be. Okay, I'm just gonna go to one of the earlier problems now that I skipped so I can see if I can solve them. Oh, this one again. Okay, great. Coplanar orbits, angular momentum. Actually, what we could do is, k is equal to 1/2 times this. Or actually, we can know. Let's do another way. So k is equal to 1/2 L squared over I. And then E is equal to 1/2 mv squared. Sorry, actually, and k is also equal to g m m over 2r, which means then that the closer it is, the higher k is. And the higher k is, the higher L has to be. Wait. Yeah, okay. So then for C should have the highest L, B should have the second highest, A should have the third highest. I think. Okay, what else did I skip? Did I skip just that one? Oh, and I skipped this one as well. Okay. Batman, who has a mass of, let's see the time, 16 minutes. Nice. Who has a mass of m equals 100 kilograms, climbs the roof of a 30-meter building, lowers one end of massive rope to his sidekick Robin. Approximate total work Robin. Actually, the total work, so it doesn't count. Also mean the work he's done on himself. Okay, so then that would also be 1,000 times 30. So that's 30,000 plus 22,500, which is 52,500. Hmm. Okay, I'm just gonna go with this and hope it is correct. Okay, actually, let's see if there's anything else I skipped. Okay, so B, A, E. I didn't skip that. Okay. Oh, okay. Shoot, I need to do this. Okay, period of star for star of mass 3m. Well, actually, we can use Kepler's third law, I guess. So I think it was t squared is equal to 4 pi squared over gm times a cubed. Yeah, okay, I have no idea how to do this actually. So, I have a feeling that it is C, because I think this 3 should be here, but we shall see, no pun intended. Okay, let's just do this one. A uniform rectangular wood block of mass m with length b and height a rests on incline shown the incline, and the wood have a coefficient of static friction u sub s. The incline is moved upwards from an angle of 0 to an angle of theta. At some critical angle, the block will either tip over or slip down. Determine the relationship between a, b, and us such that the block will tip over and not slip at the critical angle. Okay, let's see. So we have m. Well, we know that mu s, or friction, is just mu s times m g cosine theta. And for it to not slip, it would have to be greater um, than mg sine theta, which means that mu s is greater than tan theta. Okay. Hmm. Well, actually, what we could do is, I think we could do this by looking at torque. So let's pretend we have some plane here, and I kind of have to tilt my head, but let's say this is the y-axis and this is the x-axis. Well, let's say this is the pivot, so then this would be the origin, so 0, comma 0. Yeah, and this force, this side here would be a over 2, and this, dang it, how do I do this? Okay, so, okay, then this triangle here is similar to this big triangle, so this angle here is theta. And so okay, yeah, this is getting a little trickier than I anticipated. Um, okay, let's actually just see if we can get an next problem. Okay, these axles are constrained to be vertical at all times, so the discs can pivot frictionlessly on the rods. The discs have identical thickness and are made of the same material but have differing radii. The disks are given angular velocities of omega 1, omega 2 respectively and brought into contact at their edges. After the disks rotate via friction, it is found that both disks come exactly to a halt. Which of the following must hold? Okay, so I guess we could use law of conservation of angular momentum. So for this system, the total angular momentum would be well, okay, so moment of inertia is 1/2 m. Or sorry, okay, so we'll call this m, and then this is so m rho v. So then m prime would be rho. So this is rho. Um, Dang, okay, so the volume of this would be actually let's just look at the thickness. So it would be let's look at the surface area density. So it would be length times surface area density or length times area, my bad. Uh, shoot. Okay, so that would be pi r1 squared. So m prime would be pi l pi r2 squared, which would then be m times r2 squared for r1 squared. And yeah, okay, so the moment of inertia of this disk is just 1/2 mr1 squared. So the angular momentum would be this times omega 1, and the moment of inertia of the second disk has to be it has to also be, or it's 1/2 times, now it's r2 squared over r1 squared squared. Oh wait, no, okay, sorry. This times m times r2 squared times omega 2. And I think we have to set these equal to each other so that the momentums cancel out. So 1/2 m r1 squared omega 1 is equal to 1/2 r2 squared over r1 squared m r2 squared times omega 2. Okay, so first we can get rid of the 1/2s and then the m, and so 1/2 and we can also get rid of, actually no, we can't get rid of r1 squared. Okay, so we eliminate the 1/2 m from both sides. So now we have omega 1 r1 squared is equal to, actually let's change this to r1 fourth because the denominator for the other side is r1 squared, but we can preemptively move that over. r2 fourth times omega 2. And so our answer is E. And that was actually not that bad. Okay. Much time. Oh shoot, okay. That is not looking good. So I'm trying to find a way to do this, but it looks like it could take a while. Okay, so for if it tips over, we know that the torque has to be, or sorry, the gravitational force has to be to the right of the center of mass, right, and then yeah. Okay, yeah, I don't think I'll be able to solve this one. I sort of know like what method to use, but I don't know the exact steps. Okay, so if we had a really thin one, then the gravitational force would look like this, and it would definitely tip over. But in this case, it would not tip over. So we have to know what, like, actually, you know what? These are similar triangles. Okay, so this is theta, then this has to also be theta. Shoot, okay, what was I thinking? Which means then that B has to be less than A cosine theta. Yeah, okay, I do not know. I'm feeling I'm sort of on the right track, but I'm going to have to guess that it is. So let's use process of elimination here. Okay, so we would want for it to tip over, it has to be like this, where A is significantly greater than B. So this, okay, so this would be negative, first of all, so that's not right. This would also be negative. So this, well, if it's less than, then it could be anything which is less than. So it could be like no friction, in which case it would slide down. So it's either one of these two. Um, hmm. Okay, this is tricky. Oh wait, okay, this is theta. So tan theta. Tan theta is opposite over adjacent. So it's B over A, okay. Wow, oh wow, okay, I just clutched it. Because I didn't see that earlier, and then now I was like, I realized the similar triangles, and wow, okay. That was a close call, but that is all the answers with like 30 seconds to spare. And wow, okay, I think I actually feel pretty confident that I did well on this one. Okay, so let's correct it. So, and I mean, it is 2009, so it shouldn't be like terribly difficult. Okay, so I know that's correct. So for number one, it is +1. So 1 for 1, not bad. For number two is A, and oh, okay, rip. Well, that's not right. Okay, so 2. Let's mark this wrong. Okay, never mind. My confidence just went down. Okay, 3 is my second correct one, so it's +2. 4 is A, and I got A, so 4 is also +3, because I'm going to do it one by one. And for 5, I got B, and the answer is A. Okay, it's not good. 6, I got E, and it's actually C. 7, I got B. 7 is B. Okay, never mind. It appears that I actually did good on the later ones, but not as well on the beginning ones. Okay, 8 is D, so that's correct. I know I got that right. Okay, so those are 3 right. So then I said I have 4 right. Okay, so this is +5. This is +6. And this is +7. Okay, and then for 11, I said it's A. Okay, actually, I'll do A, C, H, no, A, C, B, E. And that's correct. That's correct. That's correct. And that's correct. Okay, wow. So, how many did I say I had? 7. So, that's +8, +9. I don't know what the cutoff was back then, but currently a cutoff of like 15 to 17 is considered to be like a really good score. Okay, 10, 11. Okay, now 15 is C. Okay, never mind. Oh, that's not right. Okay, and 17 is indeed D. So this is 12. 18, I said, is E. And here is also E. 19, I said was B. And 20, I said was. Yeah, I know these. I only got all 3 of these. So then it should be 12. Yeah, I'm doing. For some reason, I did better on the later ones. I guess it was because I was more cautious or something. I'm not sure. 15 for 20 is not bad. I guess. 21 is D. 22 is actually A. Okay, so this is +16. 23 is D. Huh. Why is it D? Um, hmm. Okay, never mind. Okay, so that's wrong. And yeah, 24 is right and 25 is wrong. Okay, so then 24 is 17. So I do not know how this compared to today's test. Maybe it might have been about the same, maybe a bit easier, but 17, which if I did take this today, it would have been at the cutoff. So we have 17. Not too bad. Okay, so yeah, that is it for this video. And yeah, so I hope you found this helpful. And I'll try to do more of these contests. So yeah, 17 on this one. And yeah, I hope you enjoyed this video and found it helpful. And peace.